Hello everyone, welcome to the live interaction session for the course Semiconductor Device Modeling and Simulation. So this is week 7. I will start the session. In the meantime, people can join. Okay. So let me introduce myself first. I am Ananya, a PhD scholar in the Department of Electrical Engineering, IIT Kanpur. My specialization is microelectronics and VLSI. So today I will discuss some of the problems on topics those were covered in week 7, like the content. Those are mainly Maxwell's equation and Boltzmann transport equation related to transport of and carrier movement in semiconductors. Okay. So this is week 7. I will start with the first question, that is on electromagnetic field and transport. Okay, I'll write the question first. So the question is, when the rotational path of magnetic field intensity is 0, then the current in the path will be, so what will be the current? So the options are A, 1, zero, option C is infinity, and D is 0.5. Okay, let's consider these options are in ampere. Let me use a different color for answer. So to solve this question, we will use Maxwell's equations. Okay, let me first write down the 4 Maxwell's equation. I will write it here maybe. So the first equation is del dot D equal to rho. Second equation is del dot B is equal to 0. Third equation is the curl equations, del cross E equal to minus del B by del T, and the fourth equation is del cross H equal to J plus del D by del T. Okay, so I am using the notations which were given in the lecture material. So what these parameters mean: E is electric field or electric field intensity, D is displacement field, V is magnetic field, H as given, I'm using the notation given in the lectures, magnetizing or induction field. J is the current density, and rho is in the first equation is the charge density. Okay, so for this question we will use the fourth equation. So this is known as modified Ampere's law. So the Ampere's law is modified to so that it satisfies the continuity equation. So this is the equation we are going to use. Okay. So in the question it is given that H is 0. Okay, H is a vector. So there are vector notations here I'm not using, but H is a vector. Magnetic field intensity is 0. It is given in the question. Okay, and let's consider there is no displacement field, so del D by del T is also 0. Then what will be the current? So what will be the current density? J. So del cross H will be also 0. Okay, and therefore current is also 0. So the J is also 0 if there is no displacement current, and del D by del T is if 0. So if J is 0, therefore current is also 0. If current density is 0, then current is also 0 in the rotational path. So the correct answer is option B, that is 0. Okay, before going to the next question, let me check. So let's go to the next question. This is again on electromagnetic field. So let me write down the question first. Okay. So the expression for flux density D is given. It is at 12 as 12x minus 7z. So it is a vector quantity, and we have to calculate the charge density rho. Okay. So the options are given as A 19, B 5, C minus 5, and D minus 90. Okay. I'm saving the slides so that I can share it later. What else? Okay, so let's go through this question. Find the charge density. So we have to calculate charge density. Okay, charge density is denoted by rho, so we have to calculate rho, and the function of flux density D is given as this form. Okay. So again we use Maxwell's equation. D is given as 12x minus 7z. Okay. So the equation that we will use is the first equation, del dot D equal to rho. Okay. So that Maxwell equation, the first Maxwell's equation, that is actually Gauss law. Okay. So from Gauss law we know that del dot D equal to rho. Now what will be del dot D for our case? So this operator means del D by the partial derivative, del D by del x plus del D by del y plus del D by del z, and the output is a scalar quantity. Okay. So del D by del x will be 12 plus del D by del y will be 0, and del D by del z will be minus 7. So this is 5. Okay. So our answer is charge density rho is equal to 5 units. So units are not given, so I'm just writing as units. Typically this unit will be coulomb per centimeter cube. Okay, so our answer is B, 5. Okay. Let's go to the next question. This question is on Fermi level. Okay. So the transport of carriers depends on the number of carriers those are available to move freely. Okay, and that depends on the Fermi level inside the material. So there are few questions related to this in this session. So I'll go through this third question, that is on Fermi level. Okay, let me write down the question first. Okay, so the question is, if excess charge carriers are created in the semiconductor, then the new Fermi level is known as quasi-Fermi level. So this statement is true or false? That is the question. So the answer is, it is true. So if there are excess carriers are present, that means the material or the system is not in equilibrium, then the Fermi levels are not same for electrons and holes, and those are known as quasi-Fermi levels. Okay, this we have discussed earlier also and was discussed in the lectures also. So the answer is A, that is true. Now let me give some idea about quasi-Fermi level also. So quasi-Fermi levels, these are defined when excess carriers are present in the system or the system is in out of equilibrium. Okay. Defined when excess carriers are present in a semiconductor. So when there are excess carriers, it is not in equilibrium. And the quasi-Fermi levels, those are denoted as Fn and Fp. So these are quasi-Fermi levels. So this is for the electrons, and this is the Fermi level for the holes. Okay. So in this situation, Fn and Fp, those are not equal. If there are no excess carrier, the system is in equilibrium, then Fn and Fp, so basically we consider as the same level, that is the Fermi level. So how we denote the typically used notations are, so I'll write down the notation for equilibrium and non-equilibrium. So in equilibrium, we use the notation N naught for equilibrium electron concentration, and in non-equilibrium, if there are excess carriers, then it will be N, which is equal to N naught plus delta N, whatever the excess carrier. In equilibrium, we denote the hole concentration as P naught, equilibrium hole concentration, and if there are excess carriers, then we denote as P, which is P naught plus delta P, the excess hole part. And in equilibrium, we define single Fermi level EF for a material, and EF depends on the doping concentration. The location of the EF with respect to EC or EV depends on the doping concentration. For example, if it is an N-type material, it will be close to EC, and if it is a P-type material, it will be close to EV. Whereas in case of excess carriers, we use quasi-Fermi level Fn or Fp, and these are not equal. Okay. What other difference when excess carriers are present and when there are no excess carriers? So in equilibrium, we can use the mass action law, that is N and P equal to N naught P naught, which is equal to Ni square. Ni is the intrinsic carrier concentration. Okay. When the system is not in equilibrium, there are excess carriers, then N and P product, the whole concentration and electron concentration product is given by Ni square exponential of Fn minus Fp by kT. So as you can see, the product is not equal to Ni square, and how much it will differ from Ni square, that is from the equilibrium position or equilibrium system, that will depend on the difference between the quasi Fermi levels, electron Fermi levels and the whole Fermi levels. Okay. In this non-equilibrium situation also we can use the familiar N and P equations, but we have to replace the Fermi levels with Fn or Fp. So the electron concentration, N is written as Ni exponential. In case of equilibrium we write as we write this as EF minus EI. So EI is the intrinsic level, which will be approximately in the middle of the band gap. Okay, equal distance from EC and EB. So this is EI. For non-equilibrium system, instead of EF we write Fn minus EI by kT. Similarly, for the holes, the hole concentration, that equation will be Ni exponential. For equilibrium case we use EI minus EF. Here we will use EI minus Fp by kT. Okay, we replace the Fermi levels with quasi Fermi levels in the expression. So this is about quasi Fermi levels. Okay. Okay, let's go through the next question. This is again on Fermi level. The question is the difference between the donor energy level and Fermi level in an n-type semiconductor. So we have to calculate the difference between donor energy level and Fermi level. So donor energy level, that is denoted by ED typically, and Fermi level is EF. So you have to calculate ED minus EF. Okay, the other difference in a n-type semiconductor, if 25% of the atoms are ionized at 300 Kelvin. Okay, so if the donor concentration is denoted by ND, okay, in the question it is given that at temperature T equal to 300 Kelvin, only 25% of the total donor concentration is ionized. Okay, so ND plus ionized donor concentration is equal to 0.25 of ND. Now this is the condition given, and we have to calculate the difference between ED and EF. Assume Fermi-Dirac distribution without the Eugen-Durussel. Okay, so if you remember ND plus equation, we have a term ZD which denote degeneration for the electrons for the donor level. So here in the question it is given, consider the Fermi-Dirac distribution without degeneracy. That means CD is equal to 1. Okay. What else is given in the question? The Boltzmann constant in EV is given 8.617 into 10 to the power minus 5 electron volt per Kelvin. Okay. In joule per Kelvin it is 1. Boltzmann constant K is 1.38 into 10 to the power minus 23 in joule per Kelvin. So in electron volt it is given. So we have to calculate ED minus EF. Okay, it is saying the difference, so I'm not sure whether it will be positive, negative, or it should be positive. ED is typically close to the EC, but that difference we have to calculate. Let me save this part also so that I don't discard everything and have to write from the beginning. Okay. So the question is, calculate ED minus EF. Okay. I might use E small d or capital D, like there may be mix up, but it is essentially the same. Okay. And ND we don't know the value, but it is given that 25% of the donor atoms are ionized. And the temperature is 300 Kelvin. So KT we know it will be 0.026 electron volt. Okay. So this will be the band diagram for the given semiconductor. This is EV, the valence band edge EC, and the middle this is intrinsic level EI. And let's say because the donor concentration, it is saying in the question, it is given that it is an n-type semiconductor, so EF will be close to EC and it will be above EI. So let's say EF is here, and ED, the donor levels will be somewhere near the EC. So this gap is actually very small. Okay, 30 milli-electron volt or so for many semiconductors. We actually have to calculate, so this is ED, we have to calculate D's energy difference. Now we will use Fermi-Dirac distribution for this question. So the Fermi-Dirac distribution is Fe equal to 1 by 1 plus exponential of E minus EF by KT. Fermi-Dirac distribution gives the probability of occupation of an electron at energy level E. Okay. Now we can solve this question by two methods. First I will show you one, and then we will verify with the second process also. Okay. So first method, say so what is given? Ionized donor. We can use the formula for ionized donor. Okay, so the formula is this is Nd plus by Nd. Okay, so it is entire material. There will be pentavalent impurity. Okay. It will donate one electron to the conduction band, and it will be Nd plus. Okay. So it is Nd plus by Nd. It is given as from the, I'm directly using the formula, you can refer to the lecture notes. 1 plus Zd exponential Ef minus Ed by Kt. Okay, so this is the formula. Here it is given that consider Fermi-Dirac distribution without degeneracy. Okay, so this expression, in this expression Zd will be equal to 1, so there is no degeneracy. Okay. Zd is the degeneracy term. This ratio is given as 25%, so that means it is 0.25. It is equal to 1 plus exponential Ef minus Ed by Kt. Okay. Now we can calculate Ef minus Ed from this expression. So exponential Ef minus Ed by Kt will be 1 by 0.25 minus 1. We can calculate this and then take log, okay, and get the final Ef minus Ed expression. Okay. Kt is 0.026 electron volt. So I'll solve this first. So here we are getting Ef minus Ed as 0.028 electron volt. Okay, the question is given in such a way that we are getting Ef minus Ed as positive quantity, but this is the typical band diagram for entire material. So here Ef minus Ed should be a negative quantity, but we I'm not sure if the doping concentration is very high maybe, or but for some reason Ef minus Ed is a positive quantity we are getting. So let's verify this with the second method also. Okay, so we already have an answer here. So here A is 0.028 electron volt, so that is our answer. But let's cross check that also. Okay. Another way we can do this, solve this question. This is by using donor distribution function. Okay, so donor distribution function, you can refer to the lecture notes again for the formula. So F donor, so here the energy level is ED, and this is given as 1 plus 1 by GD exponential ED minus EF by KT. Again, ZD is given as 1, and what will be FED? So 25% of the donors are ionized, so here the probability of occupation of that extra electron will be 75%. Okay, 25% electrons are in the conduction part and 75% are still in ED, that extra electron of each pentavalent atom. So this will be 0.75. Okay, and 1 plus exponential ED minus EF by KT. We can solve this equation to get ED minus EF. So here we are calculating EF minus ED, so this should come as negative of the previous answer, so that we are actually getting the correct answer. So 1 plus exponential ED minus EF by KT will be 1 by 0.75 minus 1. So we can take log and get ED minus EF. Let me do it here. Okay, so here we are getting as minus 0.028 EV. So again we are getting EF minus ED as positive quantity 0.028 EV. So this is our answer. Let's go to the question. So here our answer is A, 0.028 electron volt. Let's go through the next questions. So this week Week 7's lectures contains transport equation, Boltzmann transport equation, and elation time approximation. Basically, how carriers moves um, inside the semiconductor. So, and the next question is on transport. Let me write down the first. Let me write down the question first. Okay. What are the terms included in the transport equation? The transport equation means transport of carriers inside the semiconductor, and the transport equation is the Boltzmann transport equation. So this is the question, not giving any multiple choice answers. Let's directly go through it. Okay. Should they use a different kind? So here by transport equation I mean Boltzmann transport equation. Okay. So Boltzmann transport equation is used to solve the non-equilibrium carrier distribution inside a material. Okay. Boltzmann transport equation, I will write use a short form BTE for that, and what it describes how the carrier distribution is changing over time. And for carrier distribution we use certain distribution functions. For electrons we use Fermi-Dirac distribution function or Maxwell-Boltzmann distribution function depending on the situation, but we use a certain carrier distribution function. Okay, and BT deals with how this distribution changes over time. Okay. So transport means something changing with time, so there should be a time dependent term in BD. And what other terms? So let me write down the transport equation first. Okay. So there is this first term del F by del T, okay, plus V dot del RF plus F dot del PF. This is equal to del F by del T due to collision, plus the source term here, this is for generation and recombination, KT, which is a function of R position, K momentum, and T time. Okay, so here we have total 5 terms: 1, 2, 3, 4, 5. Now let's see what these terms mean one by one. Okay, so the first term is del f by del t. That indicates rate of change of f. So what is f? The carrier distribution function. For us it is Fermi-Dirac distribution. We are dealing with electrons and this is the Fermi-Dirac distribution function, and how the distribution function is changing with time. That is the first term. The second term is the diffusion term. Now how it is a diffusion term? So del RF, R is the position, R is a it has three components x, y, z. We are writing in 3D, so it has three components x, y, z, and del R by del F, that means how the distribution function varies with space. Okay. So if there is a variation in the distribution function, that means if in one position the distribution is high, that means higher number of carriers compared to some other position, then say it is 0.1 and 0.2, the distribution function value is high here, that means the concentration is high, so electrons will move. Okay, that means this term actually represents the diffusion because of the concentration gradient, and it is multiplied with the velocity of the particles, how they diffuse. Okay, so that is why the second term represents the diffusion in BT. The third term is the drift term. How it is a drift term? So drift happens when there is applied force. Okay, there is applied field like electric field. So we have studied earlier the drift current equation, where J is equal to Q mu into E. So that is the electric field. So there is some kind of field present, and that is how the drift of carriers happen. Okay, this is J. So here this F means the external force applied to the system, to the material. Okay, this F can be an electric field also, like F equal to Q into E. It can be magnetic field also. But what I want to say is that this is the external applied field term, so which gives actually which results the drift of the carriers. Okay, so this is the third term, is drift term. Fourth term is the collision time. Okay, how the distribution function is changing because of collision with respect to time. And the fifth term is the generation recombination term. Okay. So this is Z minus R. If there is no excess carriers, this term will be 0. Okay, this term will be connected. Okay, so in many materials and textbooks, so you may get these four terms as BT. So we can neglect the generation recombination time if there is no generation and recombination, and then the BT will have four terms First term is the rate of change of the carrier distribution. The second term is the diffusion term. Third term is the drift term. And the fourth one is the change in the distribution function due to collision. Let's go to the next question. So, another topic that was covered in this week 7, is the relaxation time approximation RTA. Okay. So, this is the question. We'll read the question first. In the simplest approach, the relaxation time approximation is invoked. Okay. So we use this approximation to solve the transport equation, where the total distribution function is split into, so the total distribution function means the carrier distribution function f, that is split into a symmetric term in terms of momentum, which is generally large, and a asymmetric term in the momentum, which is small. The option B is asymmetric term in terms of the momentum, which is generally small, and an asymmetric term in the momentum, which is large. Option C is an symmetric term in terms of momentum, which is generally large, and a symmetric term in the momentum, which is small. Option D is a symmetric term in terms of mass, which is generally small, and an asymmetric term in the momentum, which is small. So which is true for the distribution function f? Excuse me. Now, you can directly tell the answer, which is the correct answer, but let me give some insights also. So how BT is solved. Okay. So we have already discussed BT. So it has, let's not consider the generation recombination term. So if we don't consider that, BT will be del F by del T plus V del RF plus F del PF equal to del F by del T due to collision. Okay. So this is the Boltzmann transport equation, and we use relaxation time approximation for this term, the collision term. Okay. So basically del F by del T is equal to the minus diffusion term minus drift term due to applied force. Okay, and this applied force is external. By external means some applied electric field or magnetic field, uh, not the field inside of the material that which actually leads to collision and other phenomena. So this is the external field, applied field, and third is the collision term. Now, this equation is very difficult to solve. Okay. But it is very useful because we want to know how our distribution function changes over time, how carriers moves. Okay. So we want to solve this equation, but it's very difficult to solve. So for that, actually, relaxation time approximation is used. Approximation is used, and it gives us, it basically simplify this del f by del t due to collision term, and it gives us a term called tau, that is the collision time, average collision time. So in device simulation softwares, basically BT is solved with the help of relaxation time approximation. Okay, along with the Poisson's equation. Okay. The software is used. So what the softwares do, it solves BTE to give us how the carriers move, and this is done using relaxation time approximation. Also it solves Poisson's equation to give the electric field distribution, how the fields are present inside the system. Okay. Now to solve this, what generally the assumptions are made. Okay. So here we consider the equilibrium, the distribution function is f, and the equilibrium distribution function is denoted by f naught. Okay, what by equilibrium distribution function f naught, what by equilibrium means, there is no concentration gradient and no applied fields. So there is essentially no net movements of carriers, so that distribution is known as f naught. Okay. The assumption is made to solve the transport equation is that the distribution function, the non-equilibrium distribution function f, that is not far away from the equilibrium distribution function f naught. Okay. So the distribution function f does not vary much from f naught. Okay, it does not change the distribution function, does not entirely, it's not like an entirely different form of the distribution. Okay, it still holds the shape of the actual distribution function, equilibrium distribution function f naught. That is how Boltzmann transport equation is solved. Okay, it is not used if this condition is not true. So what I mean by this condition is that, let me first write down the equilibrium condition. So it is in momentum space k. K is related to momentum, so P, which is crystal momentum, is equal to h bar k. So P and K are related, so I'm drawing the EK relation basically, which is like in momentum space. Okay, so if this is the distribution, so there are field energy states here. Okay, so this is the carrier distribution. Usually in equilibrium, it is a symmetric distribution. The carriers are symmetrically distributed. Okay. Now, when any external field is applied, external force is applied, then the distribution function will change actually, and the total distribution function is split into two terms. One is the symmetric term, that is close to the equilibrium distribution function f naught, and another is the asymmetric term. Okay, so this will distribution will change, maybe few charge carriers, maybe the number of carriers increase in this side, something will happen in non-equilibrium. So this can be the distribution function can be written in two terms. Okay, one, the symmetric term, where everything the distribution is symmetric on both sides in momentum space, and an asymmetric term that actually accounts for the external perturbation. Okay, let me write it first. If external perturbation is applied, then the distribution function will change. Okay. And the total distribution function is split into a symmetric term in momentum space. Okay, a symmetric term and an asymmetric term. So symmetric, asymmetric does with respect to the K space. Asymmetric term in momentum. So the distribution function, which is the function of position, momentum and time, this can be written as the symmetric term plus an asymmetric term. What we consider that the distribution function does not vary much from the original equilibrium distribution function. So the symmetric term is usually large. Okay. We are applying small field or small perturbation, and this is usually small. Okay. Under these conditions, mostly the software solves BT along with Poisson's equation. So now you know what the symmetric term in momentum and asymmetric term in momentum means. So the distribution function f is split into a symmetric term in terms of momentum, which is generally large, okay, an asymmetric term in momentum, which is small. Okay, so our answer is A. Okay. This is about relaxation time approximation and how software solves BT. Let me check if I'm still in the meeting here. So let's do the next question. This is on mobility. Let me read the question first. If two scattering mechanisms have the same energy dependence with mobility, okay, please remember it says same energy dependence, and two scattering mechanisms, because of this the mobilities are 0.125 meters square per volt second, and because of the second scattering mechanism the mobility is 0.25 meters square per volt second. So what will be the total mobility? The units are given as meter square per volt second, and in the options also in meter square per volt second. So let's solve this question. Now in the question it is given that mobilities are due to different scattering mechanism. So essentially our question is mobility due to various scattering events. Okay. Now to solve this problem we will use Matthiesen rule of mobility. So what is that? So according to Matthiesen rule, the total overall mobility is given as this formula: summation of 1 by mi for ith scattering mechanism and inverse of that. Okay, so in our question mu1 we have two scattering mechanisms, so mu1 is given as 0.125, okay, meter square per volt second. Mu2 is given as 0.25, okay, meter square plus volt second. So let's calculate the total mobility because of these two scattering mechanism. 1 by 0.125 plus 0.25 inverse. I'm not worrying about the units because for mu1 and mu2 also the units are same, and in the options also the units are given in terms of the same unit, meter square per volt second. So what will be the answer here? So the answer here after calculation is 0.083 meter square per volt second. So do we have the answer? Okay, in the options, okay, so this is option D. Okay. If you forget the to take the inverse here, we'll get the answer as 12. So this is given in the first option itself. Okay, so you have to be careful here. Okay, now here you can see that mobility is less compared to this two term, and it is close to the smallest mobility term, the smaller one, that is 0.125. so from the equation itself you can see that the overall mobility will be dominated by the smallest mobility term. Okay, that means the scattering mechanism which has smallest mean free time. Okay, so mu is mobility is written as q tau by m, right? So maybe it is mn star or mp star, depends on if it is electron mobility. So this tau is the mean free time. So smallest mean free time will give smallest mobility, and that will actually dominate the total mobility. So I'll write this statement here also. Overall mobility is dominated by smallest mobility value. That means smallest mean free time. So this is about Matheson rule of mobility. let's go to the next question. Question 8. This is again a theoretical question. I will write down the question first. So there are few statements given. We have to select the correct statement, or what are the correct statement. There may be more than one true statement. Okay, so the statements are: the vibrations of the crystalline lattice give rise to phonon scattering. This is the first statement. The vibrations of the crystalline lattice give rise to phonon scattering. The second statement is: when neighboring atoms in a lattice oscillate in the same direction, this give rise to the acoustic bands in the phonon spectra. The second statement is: when neighboring atoms in a lattice oscillate in the same direction, this gives rise to the acoustic bands in the phonon spectrum. And the third statement is: when neighboring atoms in the crystal oscillate in the opposite direction. When neighboring atoms oscillate in the opposite direction, this leads to the optical bands in the phonon vibration spectra. This leads to the optical bands in the phonon vibration spectra. Okay. The options are A, statement 1, and statement 2 are correct, are true, whereas statement 3 is false. Option B is statement 1 and statement 2 are false, and statement 3 is true. Okay. Then option C is statement 1, 2 and 3 all are true. The fourth option is option D. Statement 1 and 3 are true, 2 is false. Okay, so there is a delay because of the tab, please bear with it. Okay, so these are the 4 options. Now this question is on phonon scattering, scattering and phonon scattering and different types of phonon scattering. So let's go through it. I will describe few concepts, few points related to scattering, mainly phonon scattering and lattice scattering. We've already these topics were discussed, but for to go through the question, I will discuss some of the concepts. So there are few scattering mechanisms, but we are mainly considering here 2 types of scattering. One is the lattice scattering, Another one is the ionized impurity scattering. So, scattering actually means the change in the carrier movements, okay, that in the direction or change in the velocity. So that basically related to the mobility of the carriers. Okay, scattering affects the mobility of the carriers and carrier movement. Now in the question, it is mainly on lattice scattering, so we'll focus on that. So what is lattice scattering? At any temperature, at any finite temperature, non-zero, lattice atoms vibrate. Okay, crystal atoms will be more appropriate, but you got the point. The atoms in the lattice sites. When these atoms vibrate, if any carriers electrons come into that path, so that will basically lead to the change in the direction of the path of the carrier that is actually moving. So, and if these atoms, these vibrating atoms, come into the path of any moving electron, path of any electron, then collision will happen. And carrier velocity gets randomized. It will change the carrier velocity. Okay. Now, when its temperature increases, okay, the oscillation of the atoms will also increase because of thermal energy. When the oscillations increases, so there will be more probability of scattering, because there will be more probability that electrons will come into the path of the electrons will cross these oscillating atoms. Okay, so at high temperature there will be more scattering. If there is more scattering, that means mobility will decrease. Okay, and with temperature, mobility has a dependency of T to the power minus 3 by 2. Mobility decreases according to this relation. Okay. Now this is the lattice scattering. These oscillations of atoms, these are the oscillations are of discrete amplitude, which is known as phonons. Okay. So oscillations are of discrete amplitude, and these are known as phonons. So lattice scattering is also known as phonon scattering. Okay. So here, if you can see the first statement, the vibration of the crystalline lattice give rise to phonon scattering. So the statement is true. Okay. Statement 1 is correct. The next two statements are on acoustic phonon scattering and optical phonon scattering. So what are those? So phonons can be of two types, acoustic phonon and optical phonons. Okay. So what is the difference between these two? Let's consider. So let's consider a 1D lattice, 1D crystal with bases of two atoms. So suppose this is atom 1. So this is the lattice, 1D lattice. This is atom 2. It is of different type maybe. This is again the first atom, the second atom, and it is repeated. So this is a basis. Atom 1 and atom 2. I'm considering a 1D lattice because it is the simplest case, but you can also check what happens in 2D and 3D lattices. So this is the basis with two atoms. Now in acoustic mode phonons, these two atoms vibrates in the same direction. This is atom 1 and atom 2. They both move in the same direction, either this direction or in this direction, but in the same direction. That is known as acoustic mode. Another mode is the optical mode. What happens here? So suppose one atom is moving in this direction and another atom is moving in this direction. So here atoms move in phase, that means in the same direction, and in this case atoms move in opposite phase. Okay. So this is the difference between acoustic mode and optical mode. Okay. And this is for 1D case. Similarly, we can think about 2D case and 3D case also. So the phonon band structure will be like this. If this is the Brillouin zone boundary, then typically it looks something like this. My diagram is not exactly correct, but you can see here two branches. So this is the acoustic phonon branch and this is the optical phonon branch. Okay. This is generally the omega axis or h bar omega axis. So this is related to energy as well. So these have higher energies, as these typically have low energies, but the phonon band structure looks something like this. Okay. So what was the question? When neighboring atoms in a lattice oscillate in the same direction, this gives rise to the acoustic branch. So in the same direction means in phase, that give rise to acoustic branch of phonon in the phonon spectrum. When neighboring atoms oscillate in the opposite direction, so opposite direction means out of phase, this lead to optical branch of phonon. So these two statements are also correct. So all three statements are correct basically. So here let me write. Statement 2 and 3 are also correct. So our answer is answer is C. Statement 1, 2 and statement 3 are true. Okay. I hope you got the idea about phonon scattering. Let's go to the next question. So this is again on transport. If Vk is the velocity of a carrier in the state k, so that is in momentum space, in the time interval t, the electrons moves the distance t into Vk. Okay. Thus, the number of electrons in the neighborhood of R at time delta t is equal to the number of carriers in the neighborhood of R minus delta t into Vk at time 0. Okay. Thus, the following equation represents, so Fkr delta t equal to Fkr minus delta t into Vk 0. So that is basically this statement. number of electrons in neighborhood of R, so that is the position at time delta t after time delta t, is equal to the number of carriers in neighborhood of R minus delta t into Vk at time 0. So the carriers, those were at time 0, those were at this position will move to position R after delta t, because the carriers are moving with a velocity Vk and the time is delta t. So what does equation represent? The options are diffusion induced evolution of Fk. Fk is the carrier distribution function. External field induced evolution of Fk. Scattering induced evolution of Fk. So what this means, that what it actually represents, how the carrier distribution is changing because of diffusion, because of external field, that means whether it is because of drift, whether it is because of scattering. Okay. And now how we will solve this? So carrier distribution function Fk. So we are basically interested in how the carrier distribution function f is changing, and f is a function of position, momentum, and time. Okay, here we are considering how the distribution function in momentum space is changing. So essentially the carrier distribution carrier distribution function f is a function of r, k, and t. Okay, and what f means? What it means, the probability of carriers probability of finding the carriers actually at position R with momentum p which is equal to h bar k. That's how it is related to k, and at time t. Okay, so we for electrons we use this function as the Fermi-Dirac distribution function. Okay, so for electrons we use Fermi-Dirac distribution function and by using this Fermi-Dirac distribution function we can actually calculate all the necessary parameters that we need. So how we can calculate all the necessary parameters, those were discussed. So what are the parameters we can determine using f? Basically the carrier density. Okay, carrier density, that is n, and we can also calculate current using Fermi-Dirac distribution function, or J. Okay, and then energy, and how we can calculate these parameters using Fermi-Dirac distribution function, that was discussed. You can refer to the lecture notes. Now let's solve the question. So it is given as we will use this expression fk r delta t equal to fk r minus delta t vk 0. Okay. R delta t is equal to f of k r minus delta t 0. So there is certain carrier distribution at position r, okay, at time t, so that is equal to, so this position is r minus delta t vk, there should be term. Okay. Delta t vk, this is the position, and because of this velocity these carriers will move to this position. This is at t equal to 0, this is at t equal to delta t. Okay. Now I will use Taylor expansion to solve this. So this I will write as, so you know that if it is a function we can do a Taylor expansion around suppose a, so that if it is a function then we can write this as f of a plus f dash x minus a plus higher order terms. Okay, let's neglect the higher order terms and only considering the first two terms here. We can write this expression as f of k r 0, suppose I'm considering this a here as I'm doing the expansion in terms of time, so this is delta fk by del t will be x minus a will be our delta t. Okay, I'm neglecting the higher order term, and this will be f of k r0, and this I am doing the expansion with respect to r, that means the position, so this will be, so it will be minus because of the minus sign, delta fk delta r, this is delta t vk. This side also neglecting the higher order terms, this will get cancelled, so finally we will get the expression as delta fk delta t is equal to minus del fk by del r dot vk. Okay, so this looks like the diffusion part. So del f by del r is concentration gradient, and because of concentration gradient the distribution function is changing with respect to time and how the carriers are moving with the velocity vk. So this is like the diffusion equation. So among these options here, okay, if electron moves, so for this expression this is basically the diffusion induced evolution of fk, right? So this is the diffusion induced evolution of fk. So what it means, like if I can make a picture here, is suppose if this is the kind of carrier distribution initially at time t equal to 0, so because of these distribution difference this will be, so with time it will change like this. Okay, so that intensity will like the maximum concentration that will decrease, and carriers will move, like it is moving in this direction, it will move in the opposite direction also, and it will move, and eventually there will be a uniform carrier distribution throughout the material. So that is what actually this equation denotes, a diffusion induced evolution of Fk, the carrier distribution. Okay, we still have some time. Let's go through the last question quickly. So this is the question: to get the mass conservation equation, so mass conservation from the general transport equation given. So this is the general transport equation that is given. What will be this phi, this term? Uh, whether this term will be replaced by mass of the fluid